Hi, welcome back. In this video, we're going to look at how the second derivative of a function affects the shape of the graph of the function. So let's start out with a couple of definitions and see what information we get. So we say that a function f is concave up on an interval I when the graph of f is always above its tangent lines on that interval. So let's see what that looks like. So here's a concave up graph, and I'm going to draw a couple of tangent lines. So notice the tangent lines that I've drawn so far have negative slope, but they're becoming less negative. And then here's one that has slope 0, and then positive slope, and then a little more positive. We can see that when the graph of a function is above all of its tangent lines, that also means that the slopes of the tangent lines are increasing, or the first derivative is an increasing function of x on that interval. And we know when a function is increasing, we know that that means its derivative is positive. So this means that the second derivative of f is always positive on that interval. All right, so what about concave down? So concave down means that the graph of f is always going to be below its tangent lines on that interval. So it looks like this. This is a concave down graph. Notice when I start drawing the tangent lines, they start out positive, a little less positive. The slopes are decreasing. There's a tangent line with slope 0, and then the slopes become negative and a little bit more negative. So when the graph of f is concave down, that means it's below all of its tangent lines, and that also means that the slopes of the tangent lines are decreasing. That means that f prime is decreasing on that interval. Well, a decreasing function means that its derivative is negative. So this means that the second derivative of f is negative on the interval I. All right, that's a lot of information about the graph of the function and its first and second derivatives. There's also something called a point of inflection, or an inflection point on the graph of a function. That's a point where the graph changes concavity. So if the graph of f changes from concave up to concave down, or from concave down to concave up, the point where that happens is called the point of inflection, or the inflection point of the graph. And notice that also means it's the point where the sign of the second derivative changes. So now, with all this information that we can get from the second derivative of a function, we have a couple of tests that we can use. We can add these tests to our toolkit. So the first test is just called the concavity test, or the test for concavity. It says if f double prime of x is positive on an interval, that just means that the graph of f is going to be concave up on that interval. So that's pretty easy to remember. Positive, concave up. And also it says if the second derivative is negative on the interval, then the graph of f is concave down. Fairly easy to remember this test. The other test that we can use is about local extrema. It's called the second derivative test. Remember, we already learned the first derivative test. The first derivative test said take a critical number and then check the sign of the first derivative before and after the critical number. Just check and see if the first derivative changes sign at the critical number, then you have a local max or a local min. Well, the second derivative test is sometimes useful. We could use it instead of the first derivative test. This one says if you take a critical number where the first derivative happens to be 0, so it can't work on a critical number where the first derivative doesn't exist, and you take the second derivative at that critical number, and if the second derivative is positive at that critical number, that means it's concave up at the critical number, so it must be a local minimum. So that's the the first part of the second derivative test. The second part says if the critical number, if the first derivative at that critical number is 0 and the second derivative at that critical number is negative, well, it's concave down, and that means it's a local max. Notice this isn't always useful. If your first derivative is 0 and your second derivative is 0 at that critical number, the second derivative test doesn't tell you anything. So it can't always be used. The first derivative test always works for local extrema. The second derivative test sometimes works. Here's an example of where it doesn't work. Suppose we have the function f of x equals x to the 4th. Pretend like you don't know what the graph looks like. And you find the first derivative, and the first derivative is 4 times x to the 3rd. Well, your critical number is 0, because f prime of 0 is 0, so that's a critical number. But now you want to see if that's a local extreme value. And instead of using the first derivative test, you decide to use the second derivative test, and you take the second derivative and you get 12x squared. But when you plug in 0, you get 0 again. So it doesn't tell you anything about whether or not you have a local max or a local min. But if you use the first derivative test, you just make a little sign diagram. The sign diagram for the first derivative always gives you information. So we plug in a number less than 0, like -1, plug it into the first derivative, and we get -4. So that's negative over there. And then you plug in a positive number into the first derivative, say +1, you get +4, so it's positive over there. So we see, using the first derivative test, that we do have a local min at x equals 0. So the first derivative test always works. The second derivative test, even though it's easy, it doesn't always apply. All right, now let's do an example. So in this example, we're going to sketch the graph of a function where the first derivative is always negative and the second derivative is always negative. The first derivative is negative means it's got to be a decreasing function. And the second derivative is negative means it's always got to be concave down. Here's an example. That's a decreasing, always concave down graph. All right, so what about the graph of a function where the first derivative is negative and the second derivative is always positive? So this means it's going to be decreasing but concave up. That's not hard. It looks something like that. Let's do a more complicated example. So in this example, we're going to eventually sketch the graph of f of x equals e to the arctangent of x. First, we're going to find all the vertical and horizontal asymptotes. Then we're going to find the intervals of increase or decrease. We'll find the local maximum and local minimum values and the intervals of concavity and any points of inflection. And then we'll just put all the information together to get the graph. So let's start with part A. To get the vertical asymptotes, we need to find places where the function is not defined. Well, we look at that function, e to the arctangent of x. Well, arctangent of x is defined on all real numbers, and the natural exponential is also defined at all real numbers. So there's no place where we could possibly get a vertical asymptote. So there are no vertical asymptotes for this graph. For horizontal asymptotes, we have to take the limit of the function as x approaches positive infinity and also as x approaches negative infinity. To do that, we need to remember what the graph of the arctangent function looks like. So let's graph the arctangent function. Remember, the regular old tangent function has vertical asymptotes at all the multiples, odd multiples of pi over 2. Well, that means that when you take the arctangent of x, and we had to limit our domain to negative pi over 2 to positive pi over 2, this function, the inverse tangent of x, has two horizontal asymptotes. Y equals positive pi over 2 and y equals negative pi over 2. Those horizontal lines are horizontal asymptotes. And the graph of the arctangent function looks like that. So this means that if we're looking at the horizontal asymptotes for e to the arctangent of x, so the limit as x approaches negative infinity of e to the arctangent of x is going to be e to the negative pi over 2. And as x approaches positive infinity, the limit is e to the positive pi over 2. So we do have two horizontal asymptotes for this function. Y equals e to the negative pi over 2 and y equals e to the positive pi over 2. Remember, horizontal asymptotes are horizontal lines. So we need the equation of a horizontal line. So let's look at part B. So in part B, we need to take the first derivative. So differentiating e to the arctangent of x using the chain rule. It's the derivative of the outside with respect to the inside times the derivative of the inside. So now, this part, e to the arctangent of x, well, that's always greater than or equal to 1. That could never be equal to 0. And since x squared is always positive, 1 over 1 plus x squared is always positive. So that's strictly greater than 0. All right. So, is the first derivative ever equal to 0? No, in fact, it's positive for all x. So that means that this is an increasing function on the entire real number line, from negative infinity to positive infinity. All right, so what about local extreme values? Well, because it's always increasing, that means we're not going to have any local max or any local min. It's never going to turn around. So part C was easy. Part D, we need the second derivative. So the second derivative, we're going to have to use the product rule. So it's going to be the first times the derivative of the second. The derivative of the second is negative 1 over 1 plus x squared. That's the derivative of the outside with respect to the inside. And then times the derivative of the inside, 2x. That's the first times the derivative of the second, and then we have to do plus the second times the derivative of the first. All right, so this is kind of a complicated looking second derivative. We can clean it up a tiny bit. It's e to the arctangent of x times negative 2x plus 1 all over 1 plus x squared squared. So now we want to find where this changes sign, we want to find where it's positive and where it's negative to find the intervals of concavity, and then we need to figure out, does it actually change sign, and that'll give us the points of inflection. So the second derivative, once again, it's equal to 0 only when the numerator is 0, and that's only going to happen when negative 2x plus 1 is 0, and that's only going to happen when x is 1/2. So let's make a sign diagram for the second derivative to check the sign on both sides of this place where it's equal to 0. So if x is less than 1/2, say x is 0, that means that the second derivative is going to be positive. And if x is greater than 1/2, say x is positive 1, then it looks like we plug positive 1 in and we get a negative second derivative. So that means that the function is concave up from negative infinity up to positive 1/2, and then it's going to be concave down from positive 1/2 to positive infinity. And it looks like we do have a point of inflection. So our point of inflection, the x-coordinate is 1/2, and the y-coordinate, we have to plug it in to the original function. And remember, the original function is e to the arctangent of x, so the y-coordinate is just e to the arctangent of 1/2. So we've used the second derivative, and we've also used the first derivative to get a lot of information about the graph of a function. And we found its horizontal asymptotes, and we found it had no vertical asymptotes, and we were able to now sketch the graph. So I'm just going to mark my axes with a couple of important values. So we have a horizontal asymptote at y equals e to the negative pi over 2, and another one at y equals e to the positive pi over 2. the y-intercept, when x is equal to 0, we have e to the arctangent of 0. And remember, the arctangent of 0 is 0. So the y-intercept is e to the 0, which is 1. And then we have a point of inflection at 1/2 arctangent of 1/2. And if we put arctangent of 1/2 into a calculator and then raise e to that number, so I'll put a point there. And so it's concave up and then concave down. And there's our graph. So using information we got from the first derivative and the second derivative and the horizontal asymptotes, we were able to sketch a pretty good graph. And we'll be doing a lot more graphing after we learn L'Hopital's rule, which will give us another way of finding difficult limits. All right, I'll see you in another video.